Thank you so much for the invitation. It's a great pleasure and honor to be here. So please feel to interrupt me at any moment with questions. I prepared a kind of rather fast-paced talk, so I will skip over details and I'll be very happy if you interrupt me with some clarification questions. Probably the simplest way of defining scalar curvature is by considering a point P, an exponential map, and using normal coordinates, computing the volume of an image of a ball of radius r. If we Taylor expand it, then we'll see that up to the 0th order, it will coincide with the volume of Euclidean ball of radius r. So this is volume of ball around point 0. Rn. And then the correction term, the lowest order correction term, will be precisely the scalar curvature times some constant times r squared. So if we have a manifold of positive scalar curvature, then we have a very simple way of characterizing it as a manifold where sufficiently small balls have volumes smaller than Euclidean volume. And there are two things that I find quite surprising about this way of defining positive scalar curvature. The first thing is that it seems that I'm not aware of any cases where somebody directly used this definition to prove anything about positive scalar curvature. And the second surprising thing is that in a somewhat roundabout way, this definition led to developments in metric geometry, which in turn turned out to be quite useful for some applications in positive scalar curvature, and are also interesting in their own right. So there's this kind of surprising usefulness and uselessness of this way of looking at, of this way of defining positive scalar curvature. So let me be a bit more precise. So we have this way of characterizing positive scalar curvature as very small balls having volume less than Euclidean, but we could also fix some particular scale r and some particular constant epsilon, which doesn't have to be the volume of the unit ball, could be something smaller, and demand that the volumes of that radius are less than that. And we can call this, because of this analogy, we can call this positive macroscopic scalar curvature. So this seems like a rather naive, simple characterization. Doesn't have to apply to a manifold. We could use it, for example, for metric space with volume replaced by Hausdorff measure. So it is quite interesting that there is an interesting back and forth between properties of metric spaces or manifolds with this positive macroscopic scalar curvature and properties of positive scalar curvature manifolds. So let me illustrate it with two examples to give you a little bit of motivation. So there is a celebrated result of Shane, Yao, and Gromov that the N torus does not admit the metric of positive scalar curvature. And there is a corresponding macroscopic positive scalar curvature property that if you have a torus with any Riemannian metric, then the universal cover does not admit positive macroscopic scalar curvature at scale r with constant for n to the power minus n. So it's a certain constant that's smaller than the volume of the Euclidean ball, which is something like n to the power minus n over 2 or something like that. If you could prove a result like that, which was conjectured by Gromov for omega n with a constant equal to the volume of the unit ball, then that would be a very strong result. It would in particular imply the usual draw conjecture, but would somehow imply it on all scales. You can always find a ball of any radius whose volume is greater than the volume of Euclidean ball. Interestingly, it's open even in dimension 2, this sharp generalized draw conjecture. Okay, and there is another result of similar nature where we have more, you have somewhat a stronger result in the macroscopic world, but somewhat limited result in lower dimensions for usual positive scalar curvature. So another Gromov's conjecture states that manifolds with higher homotopy groups equal to 0 don't admit metrics of positive scalar curvature, and without some additional topological conditions, it's only known in dimensions 3, 4, and 5. But for the macroscopic counterpart, we have it in all dimensions, again with some optimal constant here. So there's this interesting connection that the methods of proofs for positive macroscopic scalar curvature often involve some ideas about something like minimal surfaces, which also plays a role in the lower dimensional proofs on the left part. But I think to kind of understand this connection more explicitly, we need to define the notion of simplicity, of geometric large-scale simplicity that we expect positive scalar curvature manifolds to have, and that we also see for this positive macroscopic scalar curvature. So this notion of smallness. I guess our intuition is that if you have positive curvature, then the manifold should be small in some sense. So for positive Ricci curvature, that means that we have small diameter by Bonnet-Meyer's theorem, and also that if you pick a point and consider balls of radius r around that point, then their volumes and their boundary areas will be smaller than the corresponding volumes and boundary areas in the round sphere of the same curvature, with the same curvature bound. It's easy to see that such strong smallness properties don't hold for positive scalar curvature metrics. If you replace positive Ricci with positive scalar, then there's no hope of having such a strong condition. So the natural question then is, what does positive scalar curvature mean? So let me stop here to check if there are any questions. So one way of defining geometric smallness of positive scalar curvature metrics is using the notion of Urysohn width. So the Urysohn width can be defined as follows. If you have some space and a continuous map into some other space, then we could look at the maximal diameter of a fiber, where by diameter we mean diameter in the ambient space, extrinsic diameter, not the intrinsic diameter of the fiber itself. And then we can take the minimum over all these maxima, and that will be a certain quantity which corresponds to, looking at all the ways of chopping up our space into pieces of small diameter, taking the largest diameter for this way of chopping it up and trying to make this largest diameter as small as possible. So if you have small Urysohn K width, that means that you can map your space into k-dimensional simplicial complex in such a way that all diameters will be small.
I have one elementary question. So in your picture, in the middle, you have two connected components in the fiber. And how is the diameter measured in this case? Is it for each individual piece, or you have to go around in M from one connected component to the other?
Yes, it's for the whole thing. It's for
Okay.
the whole thing, not for each individual piece. Yes.
Mhm.
However, when we define Urysohn k-width of a manifold M, and we look at maps into simplicial complexes, we are always able to change our simplicial complex and change our map so that the fibers are connected by just adding. So this is something like Reeb graph construction.
Okay, thank you.
Right. So so this is something that we can do if we're allowing sufficiently large class of targets. So the notion of smallness that we hope positive scalar curvature manifolds to have is that their n-2 Urysohn width is bounded. And it's somehow straightforward to see the intuition here that we could take any space whatsoever and n-2 dimensional space, and we can multiply it by a sphere of small radius. And no matter what the space was, maybe it was a hyperbolic space with some very negative curvature. But if this R is sufficiently small, then this new space Mn will have positive scalar curvature. Yeah. And more generally, if you have some k-dimensional simplicial complex, you can embed it into some Rk plus three-dimensional space. You can take a boundary of a small tubular neighborhood of that and then perturb that in using the something like Gromov loss and connect some construction and make sure that it has positive scalar curvature. So we have a way of taking k-dimensional simplicial complexes and producing k plus one dimensional positive scalar curvature manifolds. And Gromov's conjecture says that geometrically, this is how all positive scalar curvature spaces look like. There's an even stronger version of this conjecture, a more recent one, that not only you can sort of foliate your space by fibers of a map into an n-1 dimensional space whose diameters are small, but you can also guarantee that the areas will be small at the same time. So for the Urysohn width, we don't necessarily need to have a very nice foliation. We don't even need to know that the fibers have the right codimension. But here, this is kind of a stronger claim that the fibers are all very nice and in fact also have small area. So I'm going to discuss some of these results for positive scalar curvature in dimension 3, which is the only dimension where we have a satisfactory resolution for these conjectures. Then we'll move to positive macroscopic scalar curvature and discuss some of these results there. And then we go back to positive scalar curvature using some ideas from macroscopic scalar curvature. Somehow at each step, we will carry over some ideas and intuition from one area, from one world to another, and then back to positive scalar curvature. So for three-dimensional manifolds that are compact, we have a proof of Gromov's conjecture. Indeed, we have a foliation by surfaces whose areas, diameters, and genus is controlled. So genus is in some sense sharp here, because this is Hilbert genus of some positive scalar curvature 3 manifolds, namely spherical space forms, which are not length spaces. So if you try to foliate this manifold, this is really what you expect to get. But the diameter and area bounds are not sharp. It's possible to get sharp area bounds if you forget about the diameter, but it seems tricky to get them both at the same time.
So can I come back to this one question I asked before? So we talked about the diameter and several connected components, but when you talk about the area, so the area is of course so the intrinsic area of sigma,
right?
am I right? And and can you replace in B the diameter also by the intrinsically measured diameter? Is then this inequality still true?
So that's a great question. I believe it should be possible to do.
Okay.
There is a work in progress with my collaborators, Davi Maximo and Regina Rothman, where we try to do that in connection to a question about the length of a closed geodesic. And it seems surprisingly difficult to do because we were having some troubles with the behavior of mean curvature flow. So that's a certain step. To produce this area bounds, we use mean curvature flow to kind of foliate everything nicely by surfaces of controlled area. And the intrinsic diameter doesn't behave as well as we'd like it to behave with respect to mean curvature flow. So somehow we're able to get short closed geodesic, but not quite able to get a foliation by intrinsic diameter. But I think it should be possible to do. So this is surprisingly harder than we initially thought. And so we can get a better genus bounds in some specific cases when it's S1 cross S2 or S3. So let me very quickly say a couple of things about proof ideas here. So the idea is to decompose this positive scalar curvature 3 manifolds into simple pieces, first by cutting along stable minimal sphere. So if we have a connect sum of different reducible components, then we can cut it by stable S2s. And then we use the key fact here is that in 3 dimensions, we have very good control on the geometry of stable minimal surfaces. So a two-sided stable minimal surface has to be a sphere or RP2. In orientable case, it has to be a sphere. And it has to have, and it will have small diameter, and it will have small area. And then we also have control on the geometry of Morse index 1 minimal surfaces. In this case, just from the Morse index 1 property, we don't have control on the genus, but the genus, we obtain control on the genus from the way we construct this Morse index 1 minimal surfaces. So we do a specific minimax construction, which comes from sort of Hilbert surface foliation. But then we do also get area and diameter bounds for these Morse index 1 minimal surfaces. So we end up with pieces that look somewhat like this. They have one component, which is some Morse index 1 surface of some controlled genus, because it corresponds to a Hilbert surface in this reducible component. And then on the other side, we have some stable two spheres. So then we can apply mean curvature flow. Well, it's a state. Okay, so it's a minimal surface. We can directly apply to it. But if it's an index one Morse, if it's Morse index one minimal surface, we can push it a little bit to the side using the first eigenfunction of the stability operator. Then its area will decrease, and moreover, it will become mean convex to the inside. So we can push it a little bit to the inside. And now it's going to be mean convex surface. Then we can apply mean curvature flow to it, and it will foliate everything, except we don't have good control on the diameter of these pieces. And then we use a construction from Gromov-Lawson's paper on bounding the Urysohn width of three manifolds with zero first homology, which allows us basically to cut these pieces into smaller chunks, and then restart the flow. And then when they become too long, we cut them again and restart the flow. And we can show that eventually it foliates everything, but also the diameter, the extrinsic diameter of that will be controlled. So that's the main idea of the proof here. The situation in the non-compact case is a bit different because in principle, you may not have any minimal surfaces, right? So you can think about a situation where you have, S2 cross array, and then you can add a hemisphere and then perturb it a little bit so it's have something that's sort of asymptotic to that. You'll get a positive scalar curvature manifold, which you can foliate by mean convex hypersurfaces. And so there won't be any minimal surfaces in a space like that. So with GTI1, we use a somewhat different strategy of sort of chopping it up using mu bubbles. So mu bubbles is a nice generalization of stable minimal surfaces where you kind of add a volume term or some integral, some function term, which forces existence of some stable solution in a certain region. Okay, so this is the situation in the three-dimensional setting. It has been quite difficult to try to push these methods to higher dimensional settings. But some inspiration came from the positive macroscopic scalar curvature world. So first of all, what can we say about the Urysohn width of manifolds with positive macroscopic scalar curvature or metric spaces with positive macroscopic scalar curvature? And there is this very straightforward connection that if you have that the volumes of all balls are bounded by epsilon n times r to the n, then you have n minus 1 dimensional Urysohn width of your metric space bounded by r. So interestingly, so there have been, this was initially conjectured by Gromov for manifolds. Larry Guth proved it in the case of manifolds. Then we proved it for more generally metric spaces. And then Panos Papasoglou gave a different proof. And our proof of this result was using ideas similar to Guth's proof, so using ideas from Gromov's proof of systolic inequality. So we somehow put this space X into some large dimensional Banach space, and then use isoperimetric inequality and filling inequality that in that large dimensional Banach space to somehow push it into certain n-1 dimensional skeleton of that Banach space in such a way that sort of when we compose all of the pushing maps, the fibers will have small diameter. And Papasoglu's proof, instead using ideas that are very similar to Shen-Yao proof of Geroch conjecture, basically using the idea of dimension reduction using minimal surfaces. He considers the space X and considers separating this space X into pieces of small diameter by some separating set, and then shows that if you try to minimize the Hausdorff measure of that separating set, then it will also have a positive macroscopic scalar curvature. And so you can do dimension reduction descent. So this is a result that tells us that if you have space with balls of small volume, then you can map it into n-1 dimensional space so that the fibers have small diameter.
But so in the Shen-Yao descent, we always have this single problem with singularities that may occur if we pass to the
right
surfaces. Why does this problem not occur in this context?
Right. Well, because you have, I mean, somehow one way of looking at it is just because you have a lot of freedom in this choice of epsilon n. So this is a not sharp epsilon n. And so you don't necessarily even have to pick a minimizer. You have to pick something which is close to a minimizer, and then it will have something close to this property at a smaller dimension level, but with the worst constant. So it gives you quite a bit of freedom in terms of this property, yes. And in fact, so the way we prove it and Papasoglu prove it, we prove it not just for Hausdorff measure, but for even we prove an even stronger result for Hausdorff content, which is potentially an even smaller quantity, where you just cover your set by a bunch of balls, and you take infimum over the sum of their radii to the power of K or N. And this is true for Hausdorff content, n-dimensional Hausdorff content, where this n doesn't have to have anything to do with the Hausdorff dimension of your space. And so it's a very, somehow, it becomes a very combinatorial argument about coverings by balls of various size. Right, but right, so going back to, so we hope to get some intuition from these types of arguments to go back and apply them to scalar curvature. And something that we don't like here is that it's n-1 dimensional Urysohn width, and we hope to get a bound on n-2 dimensional Urysohn width for positive scalar curvature. So there is a result by Hannah Alpert, Alexei, and Larry Guth from 2021, which proves a very interesting inequality for codimension 2 Urysohn width in three-manifold setting. So first, we have a condition which is like a positive macroscopic scalar curvature. So it's a bound on a ball of radius 10, on the volume of the ball of radius 10. And then it has this additional condition that if you have some loop in a ball of radius 1, then you can contract it in a ball of radius 2. So it's a certain filling radius condition. And so together, these two conditions, they imply a bound on the one-dimensional Urysohn width of manifold M. So the proof has a really pretty argument, which turns out to be very useful in other settings, in particular in positive scalar curvature setting. So maybe Alexei will talk about it in more detail, but I really like it, and I'm going to just very briefly sketch what's going on. So the idea is to pick a point P and consider balls of radius r around the point P and consider their boundary. So maybe our manifold looks something like that. Then we pick a connected component of this geodesic sphere. We'd like to say that this connected component actually has small diameter. So here we have two minimizing geodesics of length r, and we connect them to points x and y on this connected component of the geodesic sphere. And then the observation is that using area inequality, one can find here a sphere around point x of small area using the bound on the wheel. And then one can use another query inequality and consider cylinders around this minimizing geodesic gamma to sort of cut the sphere. So we'll have some kind of a sphere in here, and then we will cut it with a cylinder. And we will end up with some one-dimensional object. It could have several connected components, but let me just draw it as just one curve here. And one can show that it will be a small curve of small length. In particular, it will lie in a ball of radius 1. It will have length less than 1. And by condition 2, it means that we can fill it in. But you can pick the radii of this ball and the cylinder so that they're sufficiently large. And it will follow that this filling cannot intersect this geodesic gamma or this other geodesic, let's call it sigma, connecting x and y. So we have a curve which can be filled. On the other hand, it cannot intersect these two curves. But also this curve, let's call it C, is linked with the union of gamma, sigma, and let me call this one alpha. So we have C linked with gamma, union sigma, union alpha. So it must be that it has to intersect this curve alpha. The filling has to intersect this curve alpha, and the filling cannot lie too far. And from this, you can show that the distance between x and y is controlled, smaller than some constant, which works out to be 24. So you construct two linked curves, and your filling inequality implies that there is an inequality for the distance between x and y. So it's a very pretty geometric construction. And it is quite general. So whenever we have a situation that we can construct two linked submanifolds, and one of them has a filling inequality of this type, that we can fill it in some neighborhood of controlled size, we can use it to say something about these distances. So this argument was a key step in our paper with Otis Chodush and Chao Li, which classified some positive scalar curvature manifolds in dimension 4 and 5. So you can think of it as a kind of a generalization of the spherical conjecture in these dimensions. So if the manifold is spherical, then it cannot have positive scalar curvature. But if it is not spherical but has pi2 equal to 0, then it has to be either S4 or then its finite cover has to be either S4 or a connect sum of S3s cross S1s up to homotopy equivalence, or in dimension 5, it's even up to homeomorphism. So how do you go from this linking construction to this result? So the idea is that the key step here is that we can control the Urysohn one-dimensional width of the universal cover of our manifold. So let's say N is 4. You have PSC manifold with pi 2 of them equal to 0. And so then we claim that the one-dimensional Urysohn width of the universal cover of M is going to be finite. So once you know that the one-dimensional Urysohn width of the universal cover is finite, that severely restricts what kind of manifolds you can get. So from far away, you're looking at something that looks like a tree. And that has consequences for the kind of fundamental groups that you have. So it follows that the group has to be virtually free. Fundamental group has to be virtually free. And then from that, it's classical to show that it actually has to be homotopy equivalent to some connect sum of S1 cross S3s. And so the idea of the construction is, again, very similar. So you pick a point P, you consider geodesic spheres. You have 2 points X and Y here. And then it's possible to construct some codimension 2, so sigma n minus 2-dimensional. In our case, it will be 2-dimensional surface, which is linked with this closed curve. Then we can use minimal surfaces to fill this in. So we can minimize area among all surfaces with this boundary. And then inside here, we can use mu bubbles to construct a minimal surface, a mu bubble inside this minimal surface. And there is, again, this sort of dimension reduction going on. So you have a minimal, a 3-dimensional minimal submanifold. So it inherits some positive scalar curvature properties. You find inside it a mu bubble, and that mu bubble also inherits some properties. In particular, it inherits a bound on the diameter. And once you have a bound on the diameter and you are in the universal cover, that means you can fill it in some controlled radius. And so then we have that it has to intersect this point, and then the distance between X and Y have to be controlled. That may be a good place to stop for me.